Fusion is nature's way of getting energy out of atoms, and it's the reason the sun is hot, bright, and keeping us alive. Instead of breaking atoms apart like fission does, fusion squishes two light atoms together, usually hydrogen, to make a heavier one like helium. And in the process, it releases an enormous amount of energy. But here's the tricky part. Hydrogen nuclei don't want to get close because they have the same charge and repel each other, like trying to push two north poles of magnets together. To make them fuse, you need to heat them up to over 100 million degrees, hotter than the center of the sun, until they're moving so fast that they smash into each other and stick. This turns the gas into plasma, a sort of wild soup of charged particles that has to be tamed with powerful magnetic fields or lasers. If we can control this process, we get nearly endless energy from simple fuels, like deuterium from water and tritium from lithium, without polluting the planet or creating dangerous radioactive waste. Scientists are trying to build machines like Tokamaks and laser fusion reactors to make this happen, and if they succeed, it would be the ultimate power source. Clean, safe, and as close as we'll ever get to bottling a star. China's experimental advanced superconducting Tokamak, EST, often referred to as the artificial sun, has made a groundbreaking achievement in nuclear fusion research by maintaining a steady-state high confinement plasma for 1,066 seconds. This record-breaking duration marks a major step toward developing sustainable fusion power, surpassing the previous record of 403 seconds set by the same facility in 2023. But why is this so important, and what does it mean for the future of energy? Nuclear fusion is often described as the holy grail of clean energy because it replicates the process that powers the sun and stars, potentially providing limitless, carbon-free energy with minimal waste. Unlike nuclear fission, which splits heavy atoms and produces radioactive waste, fusion combines light atomic nuclei, such as hydrogen isotopes, at extremely high temperatures, over 100 million degrees Celsius, to generate vast amounts of energy. However, maintaining such conditions for long durations is an immense challenge, requiring advanced superconducting magnets, precise plasma control, and continuous high-power heating. EAST, built and operated by the Institute of Plasma Physics at the Hefei Institutes of Physical Science, HFIPS, has been a global testing platform for fusion technology since 2006. In collaboration with the International Thermonuclear Experimental Reactor project, EAST's progress contributes to the development of ITER in France, the world's largest fusion experiment. The knowledge gained from EAST's record-breaking experiments will also be crucial for China's own fusion ambitions, including the China Fusion Engineering Test Reactor, CFET. What does this mean for the future? If fusion energy becomes practical, it could revolutionize the global energy landscape, replacing fossil fuels with a clean, inexhaustible power source. Imagine a world where cities, industries, and even spacecraft are powered by fusion reactors, providing energy without pollution or resource depletion. However, challenges remain, such as achieving sustained, self-sustaining fusion reactions, burning plasma, optimizing reactor materials, and scaling up the technology for commercial power plants. So, why should we care? Because the success of nuclear fusion could solve the world's energy crisis, combat climate change, and redefine the future of human civilization. The latest achievement by EAST brings us one step closer to this vision, demonstrating that fusion energy is no longer just science fiction. It is an emerging reality. The Experimental Advanced Superconducting Tokamak, EAST, is a research facility designed to explore nuclear fusion as a potential energy source. Unlike conventional nuclear reactors that rely on fission, splitting atoms, EAST aims to replicate the fusion process of the sun, where hydrogen atoms combine to form helium, releasing immense energy. This approach promises a nearly limitless and clean power source with minimal environmental impact. EAST operates as a tokamak using powerful magnetic fields to confine superheated plasma, preventing it from touching the reactor walls while sustaining the extreme conditions necessary for fusion. East's recent milestone of sustaining plasma for 1,066 seconds demonstrates progress toward maintaining fusion reactions long enough to produce continuous energy, a critical step in practical fusion power generation. Tokamak is like a magnetic cage containing a miniature sun, keeping plasma suspended while scientists refine conditions to sustain fusion without energy loss. Plasma confinement is one of the greatest challenges in fusion energy research. Achieving a sustained, high-temperature plasma state is essential to initiate fusion reactions. East recently set a world record by maintaining high-confinement plasma operation for 1,066 seconds, far surpassing the previous 403-second record set in 2023. This breakthrough indicates significant progress in stabilizing the plasma for long durations, which is crucial for future fusion reactors aiming for continuous energy production. The record was achieved by improving magnetic field configurations, plasma heating systems, and energy efficiency. If a fusion reactor is to provide practical electricity, it must operate for thousands of seconds without interruption. East's recent achievement brings the world closer to such a reality. Sustaining plasma in a tokamak is like keeping a spinning top balanced. Any misalignment causes it to collapse, requiring precise control to keep it stable. For nuclear fusion to occur, hydrogen isotopes must collide with enough energy to overcome electrostatic repulsion, allowing them to fuse into helium. This requires temperatures exceeding 100 million degrees Celsius, several times hotter than the core of the sun. At these temperatures, matter exists as plasma, where electrons are stripped from atomic nuclei. Containing such a hot and unstable state within a reactor without melting its walls requires advanced magnetic confinement techniques, such as those employed in East. In the sun, immense gravitational pressure naturally sustains fusion, but on Earth, scientists must use extreme heat and magnetic fields to replicate similar conditions. Generating fusion energy is like lighting a fire without touching the fuel, requiring a delicate balance of temperature and containment to maintain ignition. East is a part of China's broader commitment to nuclear fusion research and is directly linked to the International Thermonuclear Experimental Reactor, ITER, a global collaborative fusion project under construction in France. China contributes to about 9% of ITER's construction and operations, using East as a testbed for innovations that will be applied to ITER and future commercial fusion reactors. Experiments conducted at East provide valuable data on plasma behavior, magnetic confinement techniques, and material durability in extreme conditions. Lessons learned from East will be crucial in optimizing ITER's plasma control strategies, bringing the world closer to self-sustaining fusion energy. East serves as a prototype, much like early wind tunnel tests were for aeronautics, refining techniques before large-scale deployment in full-scale fusion reactors. East's recent achievements were made possible by significant upgrades in its plasma heating system. The device uses a combination of radio frequency waves, neutral beam injection, and microwave heating to raise plasma temperatures to fusion-relevant levels. The heating system now operates at nearly double its previous power output while maintaining stability, demonstrating improved efficiency in energy transfer and plasma confinement. Precise magnetic field adjustments further optimize plasma stability, reducing turbulence and energy loss. By improving heating methods, East reduces energy input requirements, making fusion more energy efficient and closer to practical application. Plasma heating in a tokamak is like precisely tuning an oven to achieve the perfect temperature. Too low, and the reaction won't start. Too high, and it becomes uncontrollable. Despite recent successes, significant technical hurdles remain before fusion can become a viable power source. The main challenges include maintaining plasma stability for extended periods, improving reactor materials to withstand extreme conditions, and achieving net energy gain, where energy output exceeds input. Additionally, fusion reactions produce high-energy neutrons, which can degrade reactor walls over time, requiring new materials with enhanced durability and resistance to radiation damage. Although East has sustained plasma for record durations, it still requires more energy to operate than it generates. an obstacle fusion reactors must overcome. Developing fusion energy is like perfecting a recipe for baking bread at ultra-high temperatures, requiring precise control of ingredients and conditions to achieve a successful outcome. Fusion energy holds immense potential as a long-term solution to global energy needs. Unlike fossil fuels, it produces no greenhouse gas emissions and generates minimal radioactive waste compared to fission-based nuclear power. If successfully developed, fusion reactors could provide a nearly unlimited energy supply, revolutionizing industries such as space exploration, desalination, and hydrogen fuel production. Additionally, advancements in plasma physics from fusion research contribute to breakthroughs in material science and superconducting technologies. Future fusion power plants could provide a stable and sustainable energy grid without the environmental drawbacks of current energy sources. Harnessing fusion power is like unlocking an unlimited fuel source, providing energy without the constraints of depletion or pollution. China has invested heavily in fusion research, aiming to be a leader in next-generation energy technology. Beyond East, the country is developing the China Fusion Engineering Test Reactor, CFET ITER, which will bridge the gap between experimental fusion reactors and commercial power plants. These efforts align with China's broader goals of reducing carbon emissions and achieving energy independence. By leading advancements in magnetic confinement fusion, China aims to position itself at the forefront of a global energy revolution. China's continued breakthroughs in fusion technology accelerate international efforts toward practical fusion power. China's fusion research is like building a new transportation system, laying the groundwork for a future where energy is abundant and clean. The transition from experimental fusion devices like East to fully operational fusion power plants requires further advancements in materials science, reactor design, and energy efficiency. The next milestones include achieving a self-sustaining fusion reaction and demonstrating a net energy gain. Initiatives like ITER and CFET aim to refine these technologies, setting the stage for the world's first commercial fusion power plants in the coming decades. If successful, fusion could revolutionize energy production, mitigating climate change and driving economic development. ITER's first plasma experiments, expected within the next decade, will serve as a major stepping stone toward large-scale fusion energy production. Commercial fusion development is like launching a space program, starting with experimental tests before full-scale deployment for everyday use.